Hi, Zexi, how are you?
Good, how are you?
I'm fine,
Yeah,
thank
thank you
you.
for the arrangement.
Yeah, welcome. Sorry, I was having trouble with my computer, so I couldn't talk to you.
Yeah, no problem.
Yeah. You are working at Cornell, right?
Yes.
Oh, are
That's
you
why I
already?
have to wear a mask.
Oh, are you there right now or here at Texas?
Sorry, what?
Are you at Cornell right now?
Yes. Yeah, sorry, I have to wear a mask, the university policy.
That's fine. That's fine. Okay, it's already 12:15. We can start the seminar right now, or do you want to wait a few minutes?
We can start, I guess.
Okay. Okay, can start now then.
Sure. So glad to have this opportunity to introduce my research about this previous work during my PhD about the micromotor enabled modulation of a biomolecule absorption and desorption rate. So my supervisor was Professor Donglei Fan, and this work is also collaborated with many of my previous colleagues in material science engineering from UT Austin. Okay, so during the pandemic, we are very familiar with at least these two things. On the left, it shows a lateral flow immunoassay, which is got this recording in progress notice. Okay, got it. So we have this rapid test kit for the COVID, which requires the diffusion of the antibody antigen towards the sensing site and the absorption reaction at the specific site. And on the right is the reversal process, which is a lipid nanoparticle for the mRNA drug delivery. So it's a release process from the biomolecule from the surface to the solution. So absorption and absorption and desorption are a pair of a reversal process, and plus the mass transfer. So this is like a very common phenomenon in many of the application scenarios. So today we are going to talk about a specific type of absorption desorption process. We narrow down the scope to the only solid liquid interface, and we talk about mass transfer of molecules, not large particles. So the chemical concentration is the only thing that governs the diffusion. Well, not only thing, but the diffusion is governed by chemical concentration. Yeah, so it's important to tune the rate for both absorption and desorption. For example, for the sensing application, absorption rate is desired to be as fast as possible. However, in terms of desorption for drug delivery, one may not want a very fast rate. Sometimes extended release is required. So moderate rate probably is better than a fast rate. So anyway, we need to tune the rate for both absorption and desorption for different purpose. And in particular, for the detection of extremely low concentration samples, there's a dilemma that as your sample concentration decrease, the detection time will increase dramatically. Here shows that when the concentration decrease, the analysis time will increase. This is kind of inevitable since for the low concentration sample, it requires a longer diffusion time, or it takes a longer time for a molecule to be able to diffuse into the vicinity of your sensing site. So this is something we want to address through our very special approach. Yeah, so the outline is that we have the motivation to realize tunable absorption and desorption rate. And we know this system involves mass transfer and either absorption or desorption reaction at the surface. So it's a system involves convection, diffusion, and reaction. This is for the modeling part. And in particular, we utilize micromotors, which are micro scale or even sub-micro scale, like particles that can move under certain, like either external field or the chemical field in the solution to generate mechanical motion. We want to utilize this mechanical motion to realize a tunable absorption or desorption rate. Okay, so here's the general picture of the system. We have a solid liquid interface. On the left is a solid. It could be either for sensor, the concentration at the solid part is the sensor part is low, and the concentration of the analytes in the solution is high. So this is the scenario for sensor. But for drug carrier, well, usually the concentration on the solid part is high, and it diffuses into the solution. So the solution has a low concentration. The gradient is in the opposite direction. And today, we focus on one of the scenario, which is sensing. So the concentration is low on solid side and is high in the solution. Well, they are pretty similar. So once you get some understanding from one of the scenario, you will understand the other as well. Okay, so here we introduce additional flow field in our system. That's why we involve micromotors. So in addition to the concentration profile, we first talk about the flow velocity. Yeah, so assuming your motor is moving in the solution, you can change the coordinate system. Like you look at the micromotor only. So assuming that micromotor is still and the flow, external flow is passing around the micromotor, so that you have an external flow rate pretty high, U naught, like far away from the micromotor surface. And the flow rate will gradually reduce to 0 at the solid liquid interface. This is constrained by the no slip boundary condition in most of the solid liquid interface. Next we talk about the concentration. Concentration, because we are doing sensing. So in the solution, it's a bulk concentration, C naught, as shown here, the black line. And the concentration will gradually decrease as approaching to the sensor surface. And at the surface, there's a surface concentration, CS, because the sensing is keep absorbing the analytes. So that's why the concentration will drop here. And we define three different regimes in the system. First of all, it's bulk solution. Concentration is C naught, and the flow rate is almost U naught. And the next part is the convection regime, where concentration is almost C naught, but the flow rate changed dramatically. And in this regime, it's a convection that drives the molecule motion, because the concentration gradient is too low. The diffusion doesn't play a big role. And in the vicinity of your system, close to the surface of the sensor, there's a diffusion regime where the concentration gradient is very high, and the concentration change dramatically from almost, we define it as a regime from 0.9 of bulk concentration to the surface concentration. This regime, this distance delta D, is the regime for the diffusion regime. And for the convection, we define as the distance from 0 to somewhere close to 90% of the bulk external flow rate. Okay, so next we're going to introduce a little bit about the micromotors we use for this research. So we use a rotational motion. So the micromotor just rotate along its center, like it's a spinning motion. And in our previous work, we use these kind of a fixed micromotor. It's rotating along a nanomagnet. And the rotor is made of metal nanowires with 3 segments, gold, nickel, and gold. The nickel part is used to interact with the nanomagnet to fix there. And the entire metal rod will respond to the electric field. We have 4 electrodes to generate a rotating electric field so that the micromotor can rotate under the field. And furthermore, we coat the nanomotor surface with a thin layer of silica, which can load drugs. In this case, we study a biomolecule, now blue as the analyte, and we further synthesize small silver nanoparticle on the surface, so that they have a plasmonic response to the laser, and we can use the SERS, the surface enhanced Raman microscopy, to monitor the concentration of the dye molecule at a certain location over time. Okay, so this is the molecule we are studying in this work. It's a now blue, very small molecules, has a high diffusivity of 5 by 10 to the minus 10 meter square per second. And in this case, we found out that the surface concentration, which is related to the Raman signal intensity. So we convert the Raman signal intensity to the concentration of the surface of the sensor, we found that there's an exponential decay over time. At the beginning, it's C naught with the initial concentration and gradually decay over time with a time constant of K. So this is the release rate constant that we fitted from our experimental result. So we did the observation at different rotation speed. When there's a zero speed, 0 revolution per minute up to 195 revolution per minute. It turns out that this release rate constant K increase as the rotation speed increases. Here's the log-log plot between K and omega. So there's the K is scale with omega rotation speed to the about 0.5 exponentially. And it indicates that faster the rotation, faster the release. So this is one of our early works about using mechanical motion to tune the release rate. And furthermore, we want to confirm whether the absorption for sensing application has the same effect, and we want to get a more detailed understanding. So we create another system. This time, we didn't use the nanowires. Instead, we use a diatom frost tube, which is a natural existed silica structure from the small microorganism in the ocean, and it's made of silica and have a periodic pores on the surface. So we use this one as the main body of our sensor, and we coated a half of it of the surface with a gold and nickel bilayer. Nickel layer is magnetic and it can respond to the external field. And then we use an external magnetic stir to generate a rotating magnetic field so that our microsensor can rotate with it in a small chamber. And similarly, we synthesize small silver nanoparticle on the surface so that we can use SIRS to detect the signal of the molecules. And this time we move to a different molecule, a large biomolecule of DNA with roughly 2,000 base pair. And this time the diffusivity is much smaller. It's a 2 order of magnitude smaller than the previous one. So that it has a relatively slow diffusion rate and offers we can have a relatively long observation time to detect the sensing kinetics. And here shows one example. When the DNA concentration is only 80 nanomole, it's a pretty low concentration. We found out that without rotation, it takes about 10 minutes before the SIRS signal of the specific SIRS signal of the DNA molecule emerge in the spectrum. And once we rotate it at a 630 RPM, it only takes about 3 minutes for the same peak to emerge, which indicate that by increasing the speed, we can reduce the time of detection at this low concentration for about 3-fold. And furthermore, we did a systematic investigation starting from 0 RPM up to a rotation speed of 1200 RPM. And it turns out that the characteristic time of the sensing, which means this is also the intensity versus time saturated over a period. And this also follows exponential function. And we fit the characteristic time with this tau. And turns out that tau decreased from 520 seconds down to 130 seconds when we increase the rotation speed from 0 to 1200 RPM. And we plotted in the log-log. They follows a scale law of a minus 0.4 tau scale with omega to the minus 0.4. So similarly, we observed that the faster rotation leads to a faster absorption. And then we starting to think about how to model, how to get a deeper understanding of this phenomenon. So this is a scheme I introduced before. So in terms of fluid dynamics, we only need to consider Stokes flow because the low Reynolds number of the system. And for the mass transfer, this is just a diffusion equation, diffusion term plus the convection term related to the flow. And for the absorption desorption kinetics at the surface, we utilize Langmuir isothermal, where the absorption density over time is a function with this is the absorption coefficient, and C as the surface concentration, Nmax is the maximum absorption density minus the current absorption density. And this is absorption term, And this is the desorption term. It's a kinetic balance between the absorption and desorption. And for the boundary condition, we have the diffusion rate at the interface equals to the absorption rate because the mass conservation. And also we assume like far away from the surface, like at the boundary of diffusion layer, the concentration equals to the bulk concentration. This is general, the numerical, the simulation we have done with these three equations and the boundary conditions. So first we talk about the convection and diffusion. For convection, we need to know what's the flow field profile in our system. So first of all, rotor is our micromotor is rotating, so it's spinning along the center. And if we think from the rotor is still, the flow is coming to the end at a higher rate and coming to the center at a relatively low speed. So we simplified our system into a 2D flow with a cylinder cross section, and the laminar flow is passing along this cylinder cross section. Here's what we got from the simulation after normalization. With a Stokes flow, well, everything is normalized. So when you double the flow rate everywhere, the flow rate will be doubled. It's a scalable, which is good. And then we consider the concentration profile by assuming the rapid absorption condition, which means the absorption, the concentration at the surface in the solution phase is always zero, that the sensor can absorb in a really fast manner. And far away, the flow carries a bulk concentration C naught solution towards the cylinder. And here's what we got, the concentration profile at different flow rate. At a relatively low flow rate U naught, you can see the concentration is zero at the interface, but there's a relatively large regime where the concentration gradually increases from zero back to the normal bulk concentration. We call this regime as the depletion regime, where the concentration drops. And then as the flow rate keep increasing from 10 to the minus 4 to 10 to the minus 3, we found that the depletion regime has been shrank as the flow increase. So this probably tells a lot of difference when the diffusion layer gets thinner at a higher flow rate. So here is we plotted the concentration along two different cut lines. One is vertical, the other is horizontal. So we found out that this is the concentration profile at different flow rate. As the flow rate increase, for example, from here is the lowest flow rate, this is the highest flow rate. The diffusion layer thickness getting decreased a lot, no matter you track along cut line 1 or cut line 2. Okay, so here we plot the thickness of diffusion layer over a different flow rate. It just summarize the result from these two figures. We found out that as the flow rate increased from 10 to the minus 5 to 10 to the minus 3, the thickness of diffusion layer decreased from roughly 6 micrometer to 1 micrometer. And these two speed refers to the rotational speed of 10 RPM to roughly 100 RPM. This is the range that we have tested in our experiments. And they also show a pretty nice scaling between the thickness of the diffusion layer, delta D, over the flow rate with exponential index of a minus 0.34, which also indicate that the delta D scale with the spinning speed, omega, to the minus 0.34. So higher flow rate offers a thinner diffusion layer. And we want to understand how does the thinner diffusion layer affect the entire kinetics of our absorption system. So we know that these delta D decrease as the rotation speed omega increase. And we also know that because of non-slip boundary condition, within this narrow range, the flow rate is very low and can be negligible compared with the large concentration gradient. So for the diffusion, we only consider the diffusion driven, not the convection term. And then we solve the equations from a diffusion equation and the absorption equation from a Langmuir isothermal. After doing a non-dimensionalization, we can extract a characteristic number, which is called biomolecule number, dA, which is defined as the ratio between the reaction rate, how fast the molecule absorbed to the surface, over the diffusive mass transfer rate, how fast the concentration-driven diffusion of molecule to the surface. So it turns out that the biomolecule number is proportional to the diffusion layer thickness, delta D. And the other part are all constant. Nmax is depending on your sensing surface, Ka is depending on the absorption kinetics, and D is the diffusivity of your molecule. Those are fixed. Only the delta D is changing upon different rotation speed. So we plot this figure again, but changing the delta D by replacing with the biomolecule number. Here's biomolecule number and corresponding to different diffusion layer thickness. And here is the time constant for the entire absorption kinetics to reach saturation. We found out that there's several different regimes in this plot. First of all, at a high biomolecule number, which means the diffusion layer is pretty thick here with a thick diffusion layer. The entire characteristic time is proportional scale with delta D to the square. This is indicated by the diffusion equation. So we name these area with high biomolecule number as the diffusion limited region. And on the other hand, with a very thin diffusion layer, we've noticed that the time constant is independent of the diffusion layer, which means everything is controlled only by the surface reaction rate, nothing related to the diffusion layer can change the time constant of the system. So this regime is a reaction limited. The time constant tau R is independent of the diffusion layer thickness. Okay, and what about our experimental observation? We found out that tau is proportional to omega to the minus 0.441. And also from the simulation, we know that delta D is proportional scale with omega to the minus 0.34. So it's either neither scale with it's not a diffusion limited nor reaction limited. It's something somewhere in between. So we got this time constant scale with delta D over 1.21 by combining these two experimental observations. So 1.21 is somewhere in between. And from this plot, we can get the slope of 1.21, which corresponding to a biomolecule number of roughly 20 in our system. And this biomolecule number of 20 can give us a lot of information. First of all, it's neither too high or too small, too large or too small, it's intermediate. And it also indicated that the system is more governed by the diffusion diffusion process rather than the surface absorption reaction. So this tells us that the further increase in rotation speed can still enhance the detection rate by reducing the diffusion layer. Yeah, our mechanical motion can only shorten the diffusion time, but cannot affect the reaction. So this number tells us there's still room to further improve by increasing the rotation speed. And in summary, we have demonstrated how to use a micromotor, nanomotor to enable a tunable absorption and desorption rate by varying the rotation speed. And here shows a short video showing how we assemble a rotating micro sensor into a PDM as well. And we have done the numerical simulation and scale analysis, which gives us a non-dimensional number biomolecule, tells us the relation between the reaction and diffusion. And for our system, currently we have biomolecule number roughly 20. And so that rotation speed increase, we can further decrease the diffusion layer and without higher sensing or release speed. And for applications, we hope these finding or understanding can potentially be used to address the challenge for biosensing with high sensitivity and high speed, but for low concentration. And we are trying to achieve a more precise control in terms of the drug release by finely tuning the rotation speed of our micromotors. Okay, thank you. I would like to thank the support from the funding agency as well as the efforts from my colleagues. Also, many thanks to my supervisor in the contribution of this work. And I'm happy to take questions if there's any from the audience. Thank you.
Thank you, Zexi. That was a very interesting presentation and very interesting research. Right now, I'll be asking the viewers if they have any questions. Please feel free to ask. Unmute yourself and ask the question, or you can also ask your question in the chat box.
Yeah.
Okay, I had a question, Zexi. I'm very new to this field and I don't have a lot of experience, but I was wondering when you explained how increasing the flow rate decreases the diffusion layer a lot, how does that help your sensing application?
So the reason we, well, if you have a thinner diffusion layer, it means the time cost for your molecule, especially when there's a very low concentration, to move close to the sensing site will be shortened. And that's how we aim at to reduce the detection time for low concentration sensing. And it turns out that just by rotating faster, we can realize the reduction of the diffusion layer thickness.
Okay, thank you. Okay, I have a question from the audience. From Brent, he's asking, did you say PDMS well? So
yes, let me show the video again. Yes, here, can everyone see the screen? Yeah, so this video shows, yeah, so at the beginning, this micromotor is rotating above the thin PDMS layer. And here we define a well, a PDMS well. Well, actually, this is the lower. We empty this part. And once the motor rotating close to the well, it will just sink down and stay there. That's how we assemble the motor into the well. And this area has PDMS and this area does not have PDMS.
There is another question he's asking, is there an integrated magnet below the well?
Integrated magnet below the well. Yes, like here. Let me go to maybe the first one. Okay. Yeah, here's our experimental setup. Actually, the magnetic stir is above the PDMS well, but you can also put it beneath it. It doesn't matter.
Okay.
How did you fabricate the PDMS well with a diameter of 30 micrometer?
You just need to get a mold, a silicon mold with like a pillar of 30 nanometer diameter. Then you pour in the PDMS onto your mold surface and peel it off.
Okay. If the audience doesn't have any more question, we can thank Zexi right now. Thank you, Zexi, for your wonderful presentation.
Thank you so much for the arrangement. Yeah, I'm happy to be here.
I would like to introduce our next seminar very quickly. So next on October 15th, we'll having seminar by Kyung Ho on the highly sensitive on highly sensitive capacitive pressure sensors over a wide pressure range enabled by the hybrid response of a highly porous nanocomposite. We would like to invite you for that seminar as well. Hope to see you guys again soon, and thank you, Zexi, again.
Thank you.